The next exercise is 10.4, which is based on the famous paper written by Lucas and Prescott back in the early 70s, late 60s, early 70s. This is investment under uncertainty. In problem A, on the basis of the numerous assumptions we made in the introduction to the exercise, we should describe the sequential problem of the problem, the sequential form of the problem, which, simply put, can be expanded in this way. Just the first few terms. C is a strictly convex cost function, which is the core of the theory. Back in the 60s, it was a problem, a theoretical problem, how to solve investment problems in which, how to describe and solve investment problems in which the firm was penalized in a way for rapid changes in the capital stock, and such strictly convex cost functions were one of the possible solutions. So this is the expanded version of the supremum function, the sequential problem. Just like in exercise 10.1, we need to apply the formula which is used for evaluating plans. So this is the formula we are going to use here. So on this basis, we can rewrite the very same supremum function in this way. So it's the sum of expected values of the one period return function, where the expected value is given by the integral with respect to the probability measure relevant to the problem. So this is the reason why I am referring back to page 244 again, just like in the previous exercise, because that's a good example. What we do here is evaluating plans, so no surprise, we use the same framework, the same formula as we used previously for the evaluation of plans. If the solution to the Bellman equation and the supremum function coincide, so they coincide if assumptions 9.1 and 9.2 are satisfied. So we need to check, let me correct myself, if assumption 9.1 and 9.2 are satisfied. So we need to check if these two assumptions are satisfied. Assumption, let's go step by step. Assumption 9.1. It is related to correspondence gamma. So let's see what we know about correspondence gamma. On the one hand, the capital stock, current capital stock, and next period's capital stock must be positive. So in this sense, it's okay. But we need an upper bound. At this point, actually, we have no upper bounds. For the current purposes, it suffices to say that gamma correspondence is on the real line, the positive side of the real line. Trivially, this correspondence, the correspondence defined in this way, is non-empty and measurable, and thanks to theorem 7.6, there is a measurable selection in the correspondence, so assumption 9.1 holds. Okay, so it's okay, it holds. Assumption 9.2, let's describe the one period return function in this way, where u is a utility function specified as the area under the demand function for the market. We cannot exclude the possibility that f takes either sign, so we need to refer to assumption 9.2b, so we need a specific limit. To this end, it would be great to have an upper bound. Function u is bounded. Costs are non-negative, so the cost function is bounded below. The cost function is bounded below, and consequently, one period return function f is bounded above, and the limit exists. The limit, as defined in assumption 9.2b, so the limit exists, and assumption 9.2 holds. That's great. On this basis, we can conclude that theorem 9.2 works, and thanks to the upper bound, assumption 9.3 also holds, and thanks to this fact, theorem 9.4 works. Let's have a look at these theorems. According to theorem 9.2, if theorem 9.2, if we have the subfunction in the sequential problem, and if we solves the Bellman equation, then the two functions coincide, and the plan, the optimum plan, which we receive by solving the Bellman equation, attains the supremum in the sequential problem. So once again, the solution, the planned solution to the Bellman equation attains the supremum in the sequential problem. And theorem 9.4, the plan that attains the supremum in the sequential problem, in the sequential form of the problem, this plan is the same as the plan that solves it's a plan that solves the Bellman equation, so it is optimal in the Bellman equation, And this plan can be found by solving the Bellman equation. So theorem 9.4 claims that the plan that attains the supremum in the sequential problem is optimal in the Bellman equation, and it can be found by solving the Bellman equation. That was part A of the problem. In part B of the problem, we are dealing with the value function v. We need to demonstrate the existence and the uniqueness of the function, which can we do on the basis of theorem 9.6. Plus, we need to show that value function v is strictly increasing. We can do this on the basis of theorem 9.7, and the strict concavity of the value function can be demonstrated by referring to theorem 9.8. So actually, to solve part B, section B of the problem, we need three theorems, theorems 9.6, 7, and 8. So here we need to see that all the underlying assumptions are satisfied. And if they are, then we can use these theorems to conclude that value function is existent, it's unique, it's strictly increasing and strictly concave. So let's take one step at a time. Assumption, the first necessary assumption is assumption 9.4. State space X is a convex Borel set. It is convex. So a convex set is a set in which the section interlinking two inner points is also in the set, and this assumption is satisfied. So X is a convex Borel set. Okay, that's great. The next assumption is assumption 9.5. Z, the state space for the exogenous state, it's a closed interval, so it's a compact Borel set. It's a compact Borel set, that's great. And Q, the transition function, is monotone. It is monotone and Feller. That's great. So assumption 9.5 holds. Assumption, here comes the problem. Assumption 9.6 is related to correspondence gamma, which now looks this way. It is a very basic formulation of the correspondence. So simply put, implies this relation. So X and Y are non-negative. The textbook offers a solution to the problem because according to assumption 9.6, correspondence gamma is supposed to be non-empty. Okay, it's non-empty, but it's supposed to be compact valued and continuous. So here we need to do something about the compactness of gamma, correspondence gamma. the textbook offers a way out, because in the present form this correspondence is not compact. So instead of using the previous form, let's use one of these forms. Where this relation, the depreciation rate, regarding the depreciation rates holds, and m is a very, very large positive number. So what we do here is putting a limit on the feasibility set by choosing an appropriately large positive number m. If this m is not enough, because even an investment which is greater than m, then the absolute upper bound can be the current capital stock. So in this way we can have two versions of the correspondence which are compact. Later we will examine in detail how to choose the number m, which at this point we say it is supposed to be large enough or sufficiently large, but later we will specify the way in which we can choose an appropriate m. So given this relation, we have this relation, and from this it follows, this is the capital stock that we can take along to the next period with no cost. If we set that this relation holds, then this lower bound is good, because investment next period's capital stock cannot be lower than this lower bound. So at this point we have an ad hoc solution to the problem of making the correspondence gamma a compact set. So we need an appropriately large positive number m as the upper bound, and the lower bound which is low enough not to be touched by the actual choice at any given capital stock. So okay, at this point we know that gamma correspondence is compact valued, though we don't know a thing about how to choose the appropriate number m. So later we will examine it in detail. Correspondence gamma is compact, and correspondence gamma is continuous because the lower bound and the upper bound are continuous functions. Gamma is non-empty, and as we saw, it's compact, so assumption 9.6 holds. It's okay. So next step. Assumption assumption 9.7. We need to show that one period return function is bounded and continuous. Bounded and continuous. So this is what we need to show, and the discount factor falls between 0 and 1. Okay, so let's do this in turn. We have the one period return function in this form. Where C is a strictly convex cost function. U is bounded. Utility function U is bounded. And by limiting the correspondence, the second part, this part, so it is bounded. And by limiting the correspondence, the second part of the function is also bounded. So one period return function altogether is bounded. And given the fact that function u and function c are continuous, the one period return function f is also continuous. So assumption 9.7 holds. Practically, we forced the state space for the endogenous state x into a closed interval. We have a definite lower bound and we have a definite upper bound, and even if x cannot be 0, so x is supposed to be positive, the lower bound can be 0, and the upper bound is an appropriately large positive number m. So in this way, we can make the one period return function f bounded. So, given that all the necessary conditions underlying theorem 9.6 hold, the iterating with the Bellman operator leads to a unique fixed point. So, value function v as the solution to the Bellman equation is existent, so existence is demonstrated, and unicity is also demonstrated by theorem 9.6, by showing that all the necessary conditions underlying theorem 9.6 hold, and plus policy correspondence capital G is non-empty, compact valued, and upper hemi-continuous, and lemma 9.5 on the basis of assumption 9.4 and assumption 9.5 ensures that the solution to the Bellman equation, value function v, is also bounded. That's all. We are still in section B of the exercise in the original form of the model. In the sequential problem formulation, correspondence gamma was not compact. So we made it compact in order to write the Bellman equation and to ensure the solvability of the Bellman equation. However, we have not yet checked if the restrictions we placed on the correspondence gamma do not restrict the solvability of the original sequential problem. This is what we are going to check. So we need to check, we need to demonstrate that all the possible solutions to the supremum problem, the sequential problem, are possible solutions to the max problem, to the Bellman equation. Practically, it means that we will find a lower bound and an upper bound for the possible policies of the sequential problem. We will check if these bounds are in correspondence gamma, and given the fact, we will use the fact that correspondence gamma is compact, so if both the lower bound of policies and the upper bound of policies are in correspondence gamma, then all the intermediate policies are in correspondence gamma, and in this case the restrictions on correspondence gamma we introduced in the max problem do not restrict the solvability of the max problem, so we can solve the same supremum problem from the max problem from the Bellman equation. So let's start with the lower bound of policies. Let's find this very primitive and minimalist policy for the firm. Given the definition of the cost function, we know that this low level, actually this policy means that the firm takes along the capital stock from one period to the next, and given the definition of the cost function, we know that this level, this investment level, is free. Given that there are no costs to this minimalist investment policy, only the non-negative utilities will add up. So following this policy means that the supremum is non-negative. And given the fact that it was very easy for us to find a policy that ensures a non-negative supremum, any policy with negative supremum can be excluded. So we will use a simple method. We will try to find policies which would give negative supremum, and we will use these policies to place restrictions on correspondence gamma. Okay, so this is the lower bound. Given that this policy is free, it would make no sense for the firm to follow an investment policy which is lower than this level. So we can say that in the supremum problem, this inequality holds for all possible investment policies. So we can say that this is the lower bound. This is the real lower bound for investment policies for the firm. If we use delta prime, which is higher than delta, the depreciation rate, it's gonna be true. So this inequality holds for the problem. This is the lower bound for the policies, all the policies in the supremum problem, and this is the lower bound for correspondence gamma. And so we can see that the lower bound we use in correspondence gamma, please remember, this is how we define correspondence gamma. The mysterious M will be clarified right away. So this is the lower bound of correspondence gamma. It is always lower than the actual lower bound for possible policies. So we can say that the lower bound of correspondence gamma doesn't restrict the possible solutions to the subproblem from below. Now let's have a look at the upper bound. There are two cases. In the first case, x is lower than m, and in this case, correspondence gamma is defined in this way. And if x is higher than m, then correspondence gamma is defined in this way. We will do the same. We will check the upper bounds for correspondence gamma to see if they don't bound the possible solutions to the supremum problem. To demonstrate it, we need a useful fact from the problem. You can check it in the textbook. We know that the utility function is bounded from above. By using this upper bound, we can calculate an upper bound for the subproblem, the supremum. This is an infinite sum, so it can be simply simplified. Oh, how funny I am. So we can say that it is also true. And in the end, after a few steps, we arrive at this upper bound for the supremum. This is the upper bound for the supremum. And let's use this upper bound to define m. In the first case, x is lower than or equal to m. And in this case, let's define m as a number at which the value, the supremum of the problem is negative. It's clear that in this case, investment must be lower than m. In the other case, when x is higher than m, let's define m this way. Where for all investments higher than m, the value is negative. It's clear that, again, investment must be lower than m. So if we restrict, in this case, correspondence gamma, so if we say that y must be lower than x, we don't restrict the possible solutions because x is higher than m. So if we restrict investment to be lower than x, correspondence gamma defined in this way will place no restrictions on the possible solutions to the sequential problem. In section C, we need to characterize the one period return function, so we need to find further characteristics of the one period return function. We have demonstrated that assumptions 9.1 up to 9.7 are satisfied, so we have checked that they hold, especially checking assumption 9.7, sorry, checking assumption 9.7 was problematic because of the restrictions on the state space. There we get the result that in this case, if investment cannot be higher than the current capital stock, and if the capital stock is lower than M, then next period's investment cannot be higher than M. So because of these limitations, there is an X endogenous state beyond which the endogenous state, the capital stock cannot go. So this is the reason why we can say one period return function f is bounded. So there is a unique capital stock X beyond which capital stock cannot go. So f, one period return function f, is bounded. Let's go on. Assumption 9.8. We need to show that one period return function is strictly increasing in X. We can show it by the sign of the first derivative of the function, which is, to show you some details, it's easy to make a mistake, so hopefully I can show you the correct solution, which equals to it's complicated. What we need is the sign of this function. Luckily, we know that this part of the function is positive, and we also know that cost function c is strictly increasing and convex, sorry. And these are the facts we are going to use. So what we need is to check the monotonicity of this part of the function. So what we need is characterizing the behavior of this function, of this part of the function. Let's write the first derivative of the one period return function in this way. Given that this part is positive, then we need to demonstrate that this part, the part in the brackets, is always negative or zero. If we can show that this inequality holds, then one period return function f is going to be strictly increasing in x. How to do this? The problem is cost function x is defined on the ratio of y and x, so we need to be very cautious. Let y is set at a certain level. Cost function c has two sections. In the first section, it is true. Okay, so it is also true. This is the section of the function where costs are zero. So if y is not higher, investment is not higher than the capital stock that the firm can take along with no cost. So on this section, cost function is zero. If x is such that these relations hold, then the function is zero, and most importantly, its first derivative is also zero because the function is flat, entirely flat. Along the second part of the graph of the cost function c, investment is higher than the no-cost capital stock, the no-cost investment, than the no-cost investment. So it is also true. Here, the cost is strictly positive, but no matter how high y is, it is true. Because at any x which is appropriately high, it becomes true. So if x goes to infinity, sooner or later we will reach this ratio. So if x is large enough, then this part of the function is going to be zero in the end. The only question that remains is the behavior of the function as the function of x before it becomes zero. So what we need to do is to characterize this function as the function of x by derivating the function with respect to x. So let's derivate the function with respect to x, and after a few steps, it's not too complicated, we receive this function. Because of the strict convexity of the cost function, it's positive. It is positive, and we have all the necessary facts now. Given the fact that the function tends to 0 if x goes to infinity, and given the fact that before becoming 0, the first derivative of the function is positive, so the function is strictly increasing before becoming 0, the function must be negative on this section. So altogether, we can say that this part of the function is 0 or negative, so it's non-positive. We use the fact that when x goes to infinity, the function goes to 0, and before becoming 0, it's strictly increasing, so it must be negative. So this is what we needed. So we can conclude that one period return function f is strictly increasing in x. So assumption 9.8 holds. That's great. Assumption 9.9. Assumption 9.9 is related to correspondence gamma. According to assumption 9.9, for any given z, the correspondence must be such that if x prime is higher than x. What is the problem? Let me show you a very simple figure. The upper bound of the correspondence is m, which is constant. The lower bound, and this is the problem, the lower bound is given by a strictly increasing function, and if we have x and x prime, then this is the correspondence set at x, and this is the correspondence set and at x prime. So the correspondence gamma is not monotone in the required sense. So we need another. So we cannot say that at a lower x, correspondence gamma is the subset of correspondence gamma valued at a higher x. So we need to find another way of showing that the value function v is strictly increasing. It can be demonstrated very directly. I'm sure there are multiple ways of showing that value function v is strictly increasing in x. I have chosen a very easy way. So let's write the Bellman operator of the problem. Given x1 as the initial value for the capital stock. Okay, the solution to the Bellman equation is an optimum choice for the investment for next period's capital stock. And now let's have another starting value for the capital stock. It's sure that this relation holds because f is strictly increasing in the first variable. We don't need to do anything in the other variables of the equation. So this relation holds, which is equal to or lower than the optimum choice for the problem at this higher level of the new capital stock. Okay, so we are using the fact that f is strictly increasing in the first variable. So in the end, we have this relation. So value function v is strictly increasing in its first argument. According to, we couldn't use theorem 9.7 in demonstrating monotonicity of the value function because we couldn't build on the monotonicity of the correspondence. Correspondence gamma was not monotone in the required sense. Okay, assumption 9.10. This is the concavity assumption regarding one period return function f. Hessian is the solution, is our solution to the problem. We have, once again, we have the one period return function, and we need to use the Hessian. We are going to use the Hessian to show that this function is strictly concave. Let me show you the solutions to the steps in which we are filling the Hessian with the partial derivatives of the function. Please note that the first derivative of the utility function is the market demand function, because the utility function was the area under the demand function. Alright, so this is what we have. Let's see the second derivative. Yep. And one more step. This is negative, for sure. If we derivate the function with respect to y, we have this function from which it follows that the second partial derivative is, yes, I think it's correct. I think it's correct. Okay. In the reverse, from the reverse direction, we receive the same. Yep. And I think there is only one missing function. All right. What about the signs? What do we know about the signs? This is negative, okay. It is positive, and it is also positive, of course, and this is negative. So on the basis of the signs only, we cannot say anything intelligent about the monotonicity of the one period, sorry, not the monotonicity, the concavity of the one period return function. So let's put these results into the Hessian. Okay. Okay, the same here. And we need to calculate the determinant of this matrix, the Hessian. Okay, so let's do this step by step. We have some tricky multiplications. I am trying to simplify the expression. By omitting the arguments of the functions. So yes. Yep. And as a last step, we receive this expression, which must be positive because cost function C is strictly convex, so it is positive. X cannot be 0, and market demand function is decreasing, so it is also positive. On this ground, we can say that one period return function is strictly concave. So assumption 9.10 also holds. All right, assumption 9.11, the concavity assumption on correspondence gamma. If y is in the correspondence at x, and if y prime is in the correspondence evaluated at x, then the weighted average of the points must be in the correspondence evaluated at the weighted average of the endogenous states for every appropriate parameters. All right, let's try the usual and not too complicated way of demonstration. So given that it holds, and given that it holds, then it is also true. Okay, and it is also true we can go simultaneously working with both inequalities in every step, in each step. And we can add these two inequalities, add up these two inequalities by adding up. We receive another pretty long inequality which is equal to m, and it means that the weighted average of the policies lies in the correspondence at the weighted average of the states. So assumption 9.11 holds, just like assumption 9.10 holds. Okay, so on this ground we can say that all the assumptions underlying theorem 9.8 are satisfied. So value function v is strictly concave, and the related policy correspondence g is continuous, single valued as a function. We need to demonstrate the strict monotonicity of value function v. So we need to show that value function is strictly increasing. To this end, we need in z, I mean. So we need to show that value function v is strictly increasing in z, in the second variable. To this end, we need three assumptions. So strictly increasing. To this end, we need assumption 9.13, according to which f is strictly increasing in the third variable, I mean z. One period return function, we have the one period return function in this form. Monotonicity of f in z depends on the monotonicity of u in z, because z doesn't appear in the second part of the one period return function. So we need to check how function u depends on z. Given the fact that the demand function, the market demand function, is strictly increasing in z by assumption, the area under the curve is also strictly increasing in z. So assumption 9.13 holds. Assumption 9.14. Assumption 9.14. Gamma is supposed to be monotone in z. In the sense that if this relation holds, then correspondence must be a subset of the correspondence evaluated at the higher exogenous state. And it is true, it holds. So assumption 9.14 holds, and assumption 9.15 also holds, because transition function q is monotone by assumption. So on this basis, we can conclude that according to theorem 9.11, value function v is strictly increasing in z. Theorem 9.8 has already stated that policy correspondence G is continuous and single valued. So we can say that we have the optimum policy function. What we need to show, we are approaching the differentiability of the value function. So we need to show that any optimum choice is an inside solution. We need to show, to this end, we need to show that corner solutions are not possible, or at least they are not optimal. We need to go back for a second to the way we defined M and the correspondence gamma. There we have already demonstrated that this is the lower bound for the optimum policies, and given that this relation holds if delta prime is higher than delta, then it is true. So on the lower end, there is no corner solution. And on the higher end, we saw that these relations hold, and these relations altogether ensure that there are no corner solutions to the problem. We have interior solutions. So it is true that the optimum policy function is always an interior solution to the problem. We need assumption 9.12, and it holds because f is continuous and differentiable. So according to theorem 9.7, value function v is differentiable. In part D of the problem, we need to show that policy function g is strictly increasing in x. We have the Bellman equation for the problem, which is useful for us for now because we can have the first order condition of the problem from the Bellman equation. This is the first order condition, which we can receive by derivating the Bellman equation with respect to the choice variable y. This is an equation, and by solving this equation we can receive the optimum choice for y, but we can easily realize that both functions, I mean on the left and on the right, can be charted in a figure. This is the left hand side and this is the right hand side as an expected value. Yep, and in here in the intersection we have the optimum choice. Any change in x affects the position of the marginal cost function with any given y. An increase in x reduces the argument in the marginal cost function, and because of the strict convexity, any drop in the argument of the marginal cost function triggers a reduction in the marginal cost. So for any given y, an increase in x triggers the lowering of the marginal cost function. So simply put, if there is an increase in x, there must be an increase in y. So intuitively, yes, we can say that optimum policy function is increasing in x. We want to prove it, to demonstrate it formally. Let's use the first order condition. This is the first order condition, and okay, the probability measure, and let's put the optimum policy into the first order condition. let x prime be higher than x, and let's assume that the policy function is strictly decreasing. Strictly decreasing in x. And let's play on finding a contradiction. So, okay, so now we assume that g, policy function g, is strictly decreasing in x. By using our assumption, we can say that this holds. It cannot be a strict inequality because there is a section of cost function c where c prime, the marginal cost is 0, so we cannot use a strict inequality. Please pay attention to this circumstance. So, okay, let me show you. The cost function is something like this, and if we are on this section, then here marginal cost is 0, and even if there is a change in the optimum policy as an effect of a change in x, it may not result in any change in the marginal cost. So from this, it follows the same inequality applies, and it also follows. All right. Because of the strict concavity and monotonicity of v, the value function, it follows that policy function g is increasing, which is a contradiction. So policy function is increasing. Okay. The next theorem we need to show is that the policy function is increasing, but its slope is not higher than 1. Okay, let's use a simple fact. Okay, if the slope of policy function g is higher than 1, then if x prime is higher than x, this inequality holds. If the first derivative would be 1, we would have equality. All right, so let's assume that the policy function is increasing in x is increasing, but its slope is higher than 1. Let's try to find a contradiction. Okay, then and it follows because of transition function Q is monotone by assumption. But because of the concavity of the value function, it means that we have a contradiction. So because of this contradiction, we can claim that the first derivative is not higher, is lower than 1 actually of the policy function g.